All right, so on Friday, we talked about the ideal gas law, PV equals nRT. And we just learned that it gives us a relationship between pressure, volume, temperature, and moles. Okay, because that's what really determines, you know, how big something is. Okay, let's make sure our phone's put away. Now, PV equals nRT. So, a corollary to that, or probably a precursor to that, is what's called Avogadro's principle. Yes, the same guy as Avogadro's number. And what Avogadro's principle says is that equal volumes of gases under the same conditions of temperature and pressure contain the same number of molecules. And you guys know that the hashtag symbol before it was hashtag was number. And it also means pound. So when it tells you to hit the pound key on your phone, that's the pound key. It's the hashtag key, but it also means number. The same number of molecules. Now, what that simply means is that if I have two, that's a very off. That's a balloon full of helium and an identical balloon. That's why I teach science and not art. I'm trying to make it exactly the same. Close enough. Of oxygen. This is 5 liters. This is 5 liters. What that tells me, if I have, the balloons are in the same room, they're the exact same size, they're the same temperature, the room's the same pressure, I know that there's the same number of molecules in each balloon. Because the molecules are so far apart, doesn't matter how big or small the molecules are, there's plenty of room for everything. Balloon volume is really the space between the molecules, not the molecules themselves. Avogadro figured that out. Now, why is that important? Because if I'm going to make hydrogen gas plus oxygen gas to make water, and I balance that with a 2 and a 2, I know that I need twice as many molecules of hydrogen as I do oxygen to make that work, right? But they're both gases. So if I go and I need to get the right recipe here, if I have 5 liters of oxygen, how many liters of hydrogen am I going to need to have twice as many molecules? 10. Because equal volumes contain the same number, so if I need twice as many, I need twice the volume, I just need 10 liters. So the gas volumes are going to behave, they're going to react in the exact same ratio as the balanced equation. That makes life very easy for gases. So in any equation, the volumes are going to be the same as the moles. Equal volumes contain the same number. Now, if we say that in reverse, if I say equal volumes contain the same number of molecules, if I say it in reverse, what about the same number of molecules? What's that going to mean? If I have the same number of molecules of A and B,
they have the same volume.
They're going to have the same volume. So what if I have 1 mole? If I have 1 mole of any gas, well, I have to specify the conditions. Let's just say at STP. At STP, 1 mole of any gas at STP occupies 22.4 liters. That's huge. Because that gives us a ratio. So I can say then that 22.4 liters per mole is called the molar volume. The molar volume. So what is that going to make that a conversion factor between? If you have liters and moles, what's it a conversion factor between? Volume, well, not molar mass. Volume liters and moles. Grams per mole is conversion factor between grams and moles. Molar volume is liters per mole. Avogadro's number is atoms per mole. Density is grams per liter. Whatever has 2 units on it is a conversion factor between those two things. So this now gives us a conversion factor between gas volume and STP. Now listen, when you're trying to learn something, you gotta make mental connections. We need to make a mental connection here. We need to connect gas volume at STP with 22.4. Now 22.4 liters is this much. So 1 mole, if atmospheric pressure, which is about what we are right now, if I got it down to 0 degrees and I had a gas in here, I would know exactly that there's 6.02 times 10 to the 23rd molecules of the gas in this box. I'd have 1 mole. It's a great conversion. It's an easy conversion factor for us. Okay? So it's a conversion factor between those. So if I look then at these problems over here, and it says now how many grams of oxygen gas is needed to produce 2.5 liters of gas at STP. Okay? Now this is the one you were supposed to have done, but I don't know how much you knew about this. Okay? So we've touched on it. So I see a volume, and I see STP. Ding, ding, ding. I have to think 22.4 liters per mole. Okay? I see a volume and I see STP, so somewhere around the line I'm going to use 22.4. So, I'm given 2.35 liters of a gas. So how do I take that to moles? By? Well, do I want liters to be on the top or the bottom? I want to say 1 mole over 22.4 liters, so technically I'm going to divide. So now that gives me moles of gas, okay? But we want oxygen gas. So again, what's oxygen gas going to be?
32.
Okay, well, what's the formula for it? O2, right? So I know it's going to be 32 grams per mole. So that, if I go from moles to grams, I'm going to use the molar mass. So what do I do with that one then? Where's the 32 go on that? 32 grams over 1 mole. So now I have grams of gas, which is what I'm looking for, so I can just stick a fork in it because I'm finished. So 2.35 divided by 22.4 times 32, 3.36 grams. So these are just conversions using the 22.4. Now, let's look at number 2. Probably won't, that's going to be too low. So now again, I'm looking for how many liters, and I'm given STP, so I want to think 22.4. Okay? But this time I have grams. But my 22.4 is liters per mole. So what do I take to do to grams? You use the molar mass, and it's water. So I know that that's H2O. So I'm going to say 65.2 grams times 1 mole over 18.02 grams. Everybody should just remember the molar mass of water. So now how do I go to liters?
22.4 over 1 mole.
And you do all that out, and you get what? .10 or 81.1 liters of water. Okay? So it's just gonna be, this is just the exact reverse of number 1. Number 1, you're given liters looking for grams. Number 2, you're given grams looking for liters. But 22.4 is our conversion factor between liters and moles. Now, you probably didn't get 3, 4, and 5 right either, because we really didn't know how to do that. Now, if I look at number 3, what is the density and the molar mass of a gas? Well, what is density equal to? Mass over volume. Do I know either one of those?
Yes.
I know both, right? So the mass is what? 3.55 grams, and the volume is 4.25 liters. So you just divide that out, and you get the density. Do we have an answer?
I got 0.835.
835? But now we want molar mass. Well, what is molar mass equal to? What's molar mass equal to? And it's over there. Well, I mean, what units are on molar mass?
Grams per mole.
Grams per mole. Okay? Grams, do I know either one of those? I know grams, right? So I need to find moles. So how do I find moles? Well, I have grams, I have 4.25 liters at STP, so 4.25 liters times 1 mole over 22.4 liters is equal to 0.1890, you're right. Okay, so then you just plug that in here. And it turns out to equal what, 18 point something? 18.7. Okay, so the takeaway on this one is, hey, what am I looking for? What are the units on what I'm looking for? What do I already know? What do I still need to know?